Welcome back to another exam walkthrough. We're going to be going through 2024 Jan question number 9 and question number 20. So question number 9 says, a helium atom of mass m and velocity v collides at right angles with a surface as shown. The atom bounces off the surface with the same speed but in the opposite direction. The collision takes place in a time of t. Which of the following is the mean force acting on the atom during the collision? So one of the things that is very important is we want to find the mean force acting on the atom. So to calculate this force, this is the force on the atom, is equals to the change in momentum of the atom divided by the change in time. So first of all, let's label two directions, positive and negative. So our force that's acting on the atom will act in this direction. This is the force on atom. So I'm going to put a minus sign here because you can see that the force on the atom, the helium atom, is acting in the negative direction. Now let's find the change in momentum. So initially, the helium atom is traveling in this direction with a velocity v. So the initial momentum is going to be mv, positive. And then the helium atom bounces off and travels with a velocity v in the negative direction. So the final momentum will be minus mv. This is the initial momentum. This is the final momentum. I hope that sign is clear. This is minus and this is positive. Okay. So what I can say here is that the change in momentum is the final momentum minus the initial momentum divided by the change in time. The final momentum is minus mv and the initial momentum is minus plus mv. So final minus initial. Okay. Divided by change in time, and that's going to be minus 2mv over change in t. Okay, and that's going to be minus f atom. Okay, you don't have to cancel this minus and minus out because the minus sign is important. It tells us which direction the force is acting in. So that minus sign is important right there. And this is the expression we get for the change in momentum over change in time, which is going to be equal to the force on the atom. And this matches the expression they've given us in the option D. So the answer is option D. If you change the sign convention to make this positive and this negative, it's going to give you the same answer as well. So I hope this was clear. Now let's move on to the next question. So now let's do question number 20. Particle physicists use the principle of conservation of momentum when analyzing particle interactions. Part A, state what is meant by the principle of conservation of momentum. So this is what you need to write. The sum of the initial momentum is equal to the sum of the final momentum, provided that no external force acts on the system, so the system is a closed system. But we can also write total initial momentum as well, the same thing. But yeah, this is going to be the 2-mark answer. The first mark you're going to get for writing till here, and the next mark you're going to get is this point. Okay, so make sure you understand and memorize this to secure your 2 marks. So let's talk about the conservation of momentum. How do we get it? So we know that force is equals to the rate of change of momentum. Now let's say we have a system that consists of 2 spheres. Now the external force on the system must be equals to 0. There are internal forces which would be the force, let's say this is sphere A, this is sphere B, the force that sphere A exerts on sphere B, and the force that sphere B exerts on sphere A. There are these internal forces present, but these internal forces are in the system and they cancel each other out when we consider the system as a whole. But we must make sure that there's no external force acting on the system. The external force must be equal to 0. So hence what we can say is that F external is equals to the change in momentum divided by change in time, and F external is equal to 0. So I can say 0 is equals to the change in momentum divided by the change in time. Now I'm going to multiply both sides by change in time, and what I'm going to end up with is the change in momentum is equal to 0. The change in momentum is the momentum final minus momentum initial equals to 0, and the final momentum is equal to the initial momentum. Now what I'm going to do is I'm going to write the sum of the final momentum must be equal to the sum of the initial momentum. And the reason I'm adding that is because we have object A here and object B, sphere A, sphere B, and what we need to do is we need to add their momentums and see if initial and final momentums are the same. That means the momentum is conserved and no external force is acting. So that's why this sum is important, because we have a lot of things in our system and we need to add their momentum and kind of see if the momentum is conserved or not, and that's where all of this really comes from. Okay, now returning back to the question, we can see in part B it says the cloud chamber photograph shows alpha particle tracks in helium. An alpha particle collided with a helium nucleus at X. After the collision, the alpha particle moved at an angle of 20 degrees to its initial direction as shown. Okay, and then it says, show that the speed of the helium nucleus immediately after the collision is 5.6 times 10 to the power of 6 meter per second. They've given us the mass of helium nucleus and the speed of the alpha particle after the collision. Okay, so we have the alpha particle, it's moving towards the helium, and the helium is stationary initially, and then after they collide, the helium nucleus is going to move at an angle of 70 degrees to the original direction of the alpha particle, and then the alpha particle is going to move with an angle of 20 degrees relative to the original direction it was moving at. Okay, that's kind of what's going on here, is that we have the helium here, and then you have the alpha particle moving, and then the alpha particle moves in this way, and the helium moves in this direction. Okay? Alright, so what we have to do now is we have to apply the conservation of momentum principle. But before we do that, let's make components and do that. So the initial velocity of the alpha particle, I'm going to put this as the symbol for that. And then we have the final velocity of the alpha particle. Okay, and then we have the velocity of the helium nucleus as well. And then what we can do is we can just make components of this. Okay, I'm going to say VH sine 70, and then here also VH cos 70. Same thing here, V alpha F sine 20, and then we're going to have V alpha F sine, or no, it's going to be cos 20. Okay, so that's all the components. I didn't want to do that later, let's do that now. And now let's talk about the conservation of momentum in the x direction and the y direction. Now, before you go on and try to do it in x direction, there's going to be a problem. You know this, the initial velocity of the alpha particle. And if you don't know this, you can't solve it, because you have two unknowns and you have one equation. You can't even simultaneously go for it. And even if you have two equations, still can't go for it. It's not going to work out. So that's going to be a big problem. So don't go for that, number one. Number two, go for the y direction. That's going to work for you the best. Because in the y direction, we know that the sum of the initial momentum must be equal to the sum of the final momentum. And initially in the y direction, the momentum is 0. So the final momentum, the sum of the final momentum in the y direction must also be equal to 0. Hence we can say that if this direction is positive, this is negative, then the mass of the helium nucleus sine 70, no, I forgot the velocity, one sec, VH sine 70 minus the mass of the alpha particle, the final velocity of the alpha particle sine 20 is equal to 0. So we can basically say mh vh sine 70, and that's equals to this. Okay. And now, let me just make some room. So now that we have this, we need to find the speed of the helium nucleus immediately after the collision. We just show that, so we can just write VH, that's what we need to find out. M alpha, V alpha F actually, sine 20 divided by MH sine 70. So the expression goes like this: mass of the alpha particle times the final velocity of the alpha particle sine 20 divided by the mass of the helium nucleus sine 70. That's going to give me the velocity of the helium nucleus after the collision. Okay, so now I'm just going to plug in the values and get the answer. Okay, so I've plugged in all the values. Okay, now one doubt students often have is, okay sir, we know the mass of helium nucleus, speed, well and good, but we don't know the mass of the alpha particle. Well, the alpha particle is just the helium nucleus, so you can just use the same mass. So basically the mass of alpha particle and the mass of the helium nucleus both are the same. And actually, if they are the same, you can just cancel both of them out as well. So that's going to give me an answer of 5.64 times 10 to the power of 6 meter per second, which is approximately equals to 5.6 times 10 to the power of 6 meter per second. Now let's move on to the next part. Okay, so next part is that the kinetic energy of the alpha particle before the collision was 9.01 times 10 to the power of minus 13 joules. Deduced that the collision was elastic. So just a reminder, elastic collisions, Ke conserved, inelastic, Ke not conserved. So they have given us the initial kinetic energy. Let's find the final kinetic energy. So the Ke final is equal to the Ke of the alpha particle plus the Ke of the helium nucleus when we're looking at the situation finally. Okay, right, so we have the velocity of both of them actually. So what we're going to do is plug in the values. So half the mass of the alpha particle, the final velocity of the alpha particle square, plus half the mass of the helium nucleus times the velocity of the helium nucleus square. So I'm going to plug in the values and let's see what we get. Okay, so I've plugged in all the values. You could have also factored out half m. That's up to you. So I've plugged in all the values. I get 9.04 times 10 to the power of minus 13 joules. And 9.04 times 10 to the power of minus 13 joules is approximately 9.01 times 10 to the power of minus 13 joules. And hence we can say, so the collision is elastic. Remember, the last two are very important if you don't want to lose marks. Okay, so that's going to be the answer to this question. I hope you understood it. Now I'm going to show you the mark scheme and the examiner report.